Hey everyone, and welcome to this explainer. Today, we are going to completely unravel what is, honestly, the ultimate cosmic paradox. We're talking about supermassive black holes. By their very definition, right, these are regions of space-time where gravity is just so intense that absolutely zero, not even light itself, can escape. They are literally the darkest objects in reality, and yet, under the exact right conditions, they power phenomena that completely, utterly outshine the entire galaxies that host them.
Okay, let's dive into this, because it's such a fascinating mystery. Think about it. How does a light-trapping void suddenly become the absolute most luminous engine known to modern astrophysics? Well, today we're going to explore exactly how this transformation happens. We'll break down the mechanics of these cosmic monsters piece by piece and really look at the immense, undeniable impact they have on the entire structure of our universe.
Now, to really grasp the scale of what we're dealing with here, we first got to look at how these galaxies compare to our own. Take a normal galaxy, like our Milky Way, for example. All the light you see, that's just the combined glow of billions of individual stars all undergoing nuclear fusion. But an active galaxy? Oh, that is a completely different beast. Sure, it still has stars, but its primary energy output, which we can observe across the entire electromagnetic spectrum, from intense radio waves all the way up to gamma and X-rays, comes directly from its core. The engine driving all this isn't stellar fusion. It is raw, unadulterated gravity.
Astronomers call that active core an active galactic nucleus, or AGN for short. Basically, an AGN is a super compact region right at the center of a host galaxy. And the power source? A supermassive black hole. And thanks to incredible tools like the Event Horizon Telescope, we've actually started to image these things directly. We are talking about black holes ranging from 100 million to well over 1 billion times the mass of our Sun. But here's the catch. Just sitting there being massive isn't enough to make an AGN. It has to be actively feeding. It has to be pulling in nearby gas, dust, and even whole stars in a process we call accretion.
When this feeding process is really running at maximum efficiency, an AGN can hit a bolometric luminosity, meaning its total energy output across all wavelengths, of up to 10 to the 48th power ergs per second. Now, that is a staggeringly huge number. To put it into perspective, imagine a region roughly the size of our own solar system, generating enough energy to outshine the 100 billion stars of its host galaxy by a factor of 1,000. It's just an almost incomprehensible concentration of power.
So, how does it all work? Well, here is our roadmap for today. First, we'll look at the engine and how we feed the monster. Second, the disguise, specifically the unified model. Third, the exhaust, which covers relativistic jets. And finally, the ecosystem, where we look at AGN feedback.
All right, let's kick things off with Section 1, the engine, feeding the monster.
Because gas and dust out in space have angular momentum, they don't just fall in a straight line right into the black hole. Actually, scratch that. It's more like they spiral inwards, forming this incredibly flattened structure called an accretion disk. As that matter gets closer and closer to the event horizon, it accelerates to just unbelievable speeds. And the friction? The intense friction within that disk strips away the angular momentum and heats the infalling gas to literally millions of degrees. It gets so blistering hot that it starts emitting massive amounts of ultraviolet and X-ray radiation. So the blinding light isn't coming from the black hole itself, but from the gravitational death spiral of the material just outside of it.
But here's the thing. This accretion disk doesn't always behave exactly the same way. It changes based on how fast the black hole is actually feeding. When it's gorging itself, it forms a standard thin disk. In this state, the gas is super dense, it cools efficiently by radiating photons, and that's what creates that brilliant light. But if the black hole is starving, the gas becomes diffuse and kind of puffs up into this thick, ultra-hot donut shape. It can't radiate light effectively, so all that incredible heat is just swallowed, or advected, straight across the event horizon.
Moving right along to Section 2, the disguise, the unified model.
Now, what's really interesting here is that this unified model actually solves a decades-old astronomical puzzle. See, for a long time, astronomers categorized active galaxies into this massive, confusing zoo of different objects: quasars, Seyferts,
blazars, radio galaxies. But the unified model elegantly explains that, hey, these are often the exact same physical objects. Surrounding the accretion disk is this massive, dusty, donut-shaped torus. If we happen to look at the AGN face-on, like looking straight down the hole of the donut, we see the blazing accretion disk and all those fast-moving clouds. We call that a quasar or a Seyfert 1. But if we view it edge-on, that dusty torus blocks the central glare, and we classify it as a Seyfert 2. So orientation really does change everything we see from Earth.
Okay, let's zoom out a bit for Section 3, the exhaust, relativistic jets.
In a small fraction of these AGN systems, highly collimated jets of plasma are just fired out in opposite directions at very nearly the speed of light. But how does that even happen? Well, we have two leading theories based on general relativistic magnetohydrodynamics. The first is the Blandford-Zonic mechanism. Try to think of this like a colossal cosmic unipolar generator. Extremely powerful magnetic field lines literally thread the rotating event horizon, and the black hole's spin winds them up. It extracts rotational energy directly from space-time itself to blast plasma outward. The second theory is the Blandford-Payne mechanism, which relies more on the accretion disk. Imagine a bead on a spinning wire. In this case, magnetocentrifugal forces fleeing plasma along the magnetic field lines anchored in that rapidly rotating disk.
These jets are so incredibly powerful that they can extend for millions of light years right into intergalactic space. And because of their immense size, their extremely strong magnetic fields, and those relativistic speeds, these jets act as the universe's ultimate particle accelerators. They are actually the leading candidates for the source of ultra-high-energy cosmic rays. We're talking about accelerating protons or heavy nuclei to macroscopic energies of 10 to the 20th power electron volts. That is physics far, far beyond anything we could ever hope to create in colliders here on Earth.
Let's pull all the way back now for Section 4, the ecosystem, AGN feedback.
A supermassive black hole is pretty tiny compared to its host galaxy. It's kind of like a single marble sitting in the center of a giant city. Yet the energy it releases acts as a primary thermostat for that entire city, in a process we call AGN feedback. And this operates in two main modes. In the radiative mode, the intense light from a rapidly feeding black hole drives these powerful spherical winds that sweep out the interstellar medium. It literally blows the star-forming gas right out of the galaxy. Then you have the kinetic mode. That's where those relativistic jets we just talked about inflate massive, hot bubbles in the galaxy's halo. The mechanical energy from these expanding cavities stops the surrounding gas from cooling and condensing into new stars.
So through this feedback, you'd think the black hole ultimately just chokes off its own food supply, right? Well, recent observations from the James Webb Space Telescope revealed a pretty incredible twist, a self-regulating fuel cycle. JWST looked at a galaxy named NGC 4696 and saw that after the jets heat up the galactic gas, portions of that gas actually eventually cool down, condensing into these long, narrow filaments. Magnetic forces then gently guide these cooler gas streams right back down into the accretion disk. It's essentially a massive cosmic recycling engine where the black hole creates the exact conditions needed to feed itself all over again.
It's just a beautifully intricate system. As one of our sources so aptly notes, everybody blames black holes for almost everything. And, you can really see why. The sheer physics of accretion and energy dissipation make these objects so much more than just simple cosmic vacuums. Through their disks, their winds, and their jets, they regulate star formation, they enrich the intergalactic medium, and they fundamentally dictate the life cycle of their host galaxies over billions of years. We started today with a paradox, wondering how the darkest objects in reality create the brightest light. But the real revelation here is the profound shaping influence they have over the entire cosmos. They aren't just destructive monsters at all. They are the fundamental engines of cosmic evolution, which leaves us with a pretty compelling thought to chew on. Are supermassive black holes the true architects of the universe we see today? It's a massive question, and it's one waiting for next-generation observatories like the Extremely Large Telescope and the Square Kilometer Array to fully answer. Thank you so much for joining me on this explanation, and as always, keep looking up.